Good morning, everybody, and it's a pleasure to be here, and it's a special pleasure to be invited by students, so I can't refuse an invitation by students, and so this is actually the first time I'm being here. So, Attosecond is a very short time. So, how do we access this? So the most typical way, as it has been done during the femtosecond time domain, is actually, the principle is actually shown here. So normally, what you do, you take a trigger and start an ultrafast process. And then a little bit later, you make a flash, and that gives you then the measurement. And you keep repeating that. You replace then, for example, this light bulb. Here is the trigger that is starting a very fast process, which is going through this light bulb. And you replace, after each measurement, you will see why, this light bulb, because it is a destructive measurement. So if you go with a flash of light, a typical flashlight in the old days was a microsecond, and this example actually shows you a time resolution of a microsecond. So if you keep repeating this, so trigger, you wait for a while, take a picture, you get the next. Then you repeat again, wait a little bit longer, make a flash, and you see the whole process, and at the end, you actually have a movie. So this is how you access very fast processes with light. And of course, the stroboscope shows you here, and you get a really nice detailed movie how this fast process is going, which is of course much faster than what you see with your eyes. And it is also clear from here that the whole time resolution is given by the duration of the flash of light, right? So this is another example when a bullet goes through an air balloon, and you see how the air balloon is exploding, and you can actually see, even though it's in pieces, the air balloon is still pretty much intact in its larger form. So when you want to extend this into the molecular resolution, and you want to get a much better time resolution, you then have to go away from these flashlights and go to the lasers. And so in the 70s, we learned how to produce femtosecond laser pulses. And when you have a femtosecond laser pulse, you can just take some beam splitter and a mechanical delay line so that the stronger pulse is normally then starting the ultrafast process, like that would be the bullet here. And the weaker pulse gets delayed by the time of flight and is looking at this one. So this is the flash. It can be absorption, it can be diffraction, it can some kind of optical interaction with the device on the test. And by just moving, for example, this one by 1 micron, you easily get femtosecond time resolution, but we also know that we can move stages with much higher precision, and that's why we can also access the attosecond time resolution. So when we want to get more detailed information about the molecular structure, then of course we need to have a different physical process to resolve it, so that we can combine the femto and atto or picosecond time resolution with the atomic resolution. We then combine this, for example, with a diffraction. So you have a first pulse that is actually exciting a process, and then, for example, a hard X-ray pulse that is then looking at the diffraction, and that gives you then the structure as it falls apart. And you can step nicely through this one and get the whole dynamics out of it. This is one reason why all over the world people are building XFELs to make that kind of measurements. So in the 70s and in the 80s, this kind of pump probe technique have been extremely successful. So for example, also in the semiconductors, we've learned how excited electrons, so if you look at here the energy, the density of state, and you, for example, take electrons from the valence band and bring them up in the conduction band by your pump pulse, a short pulse. Initially, these electrons are not thermalized, and so over the years we learned all the recombination processes that happened in the semiconductor, and that actually allowed us to build better lasers and better electronics and scale up things. So this here, for example, is a transient absorption spectroscopy. So the probe pulse measured the transient absorption, because when you have electrons in the conduction band, they of course affect the absorption because they occupy states. It's like band filling. And so they reduce the absorption. But if your probe pulse is very broad, you can look at it all over the place. But then the other thing is, if once you understand what is going on, and that has been always the case in ultrafast spectroscopy, first you try to understand what is actually going on in these really short time scales. Once you understand what is going on, you start changing things and controlling things. And so we've also learned that when we introduce in a semiconductor mid-gap traps, we can actually control the impulse response, the fast recovery. And some of you might recognize what this is. This was actually something that I've used for the CSEM, which allowed us to get really nice short pulses from diode-pumped solid-state lasers. But what I was mentioning, if the probe pulse can be very, very short, and we also know that means we have a very broad spectrum, we can actually look at the dynamics for the full spectrum. And this is a picture about the current attosecond transient absorption. And you can see over a huge photon energy range, this in a helium interaction, all the details in the spectrum. And sometimes people argue, oh, if you make shorter and shorter pulses, you actually lose the spectral resolution. But this is not true, because in the transient absorption, remember, you're stepping through one after the other, and then you actually look with very slow detectors, and you average for a long time. So even though you have very broad pulses, you can still resolve a lot of detailed spectral dynamics, because you just go one after the other and then put the whole information together. So it's an extremely, attosecond or ultrafast transient absorption is an extremely powerful technique to actually ultimately understand what is going on. But of course, the X-ray is another technique, and so on. There is a whole bunch of things that you can use to ultimately look at your ultrafast processes. So over the years, we pushed the pulse duration to shorter and shorter pulses. And when you look at it in terms of the dynamics on a molecular scale, you go from the micro-nanosecond, from the collisions in there, to the rotation, moving down to the picosecond, to the vibration. And so there was a lot of femtochemistry having been done in the 70s and 80s. And that actually resulted in Nobel Prize in chemistry. And when you look at the vibrational period of a very small molecule, hydrogen, the period is actually 8 femtosecond. So normally you assume that, in the femtosecond, picosecond domain, you look at the dynamics of the ions, of the atoms, of a whole molecular system. And if you move into the attosecond regime, you're actually accessing the electrons directly. And the electrons, as we know, are actually responsible for the bonding. They're ultimately driving this whole dynamics of the atoms. And normally, as a measure of the speed, of the time resolution in the attosecond domain, you take, for example, a semi-classical picture and look at the Bohr atom, and basically the period of an electron going around is about 158 attosecond, even though we know that this picture, of course, is not very accurate. So this basically tells you why we have been pushing over the years to shorter and shorter and shorter pulse duration. Okay, because the shorter the pulses, the better is your time resolution. And so this summarizes it initially in the 70s and 80s. It was all dominated by the dye laser, and the shortest pulses with the dye laser was 27 femtosecond, and only external compression got it down to 6. And then with the invention of the Ti-sapphire laser, a whole new generation of people came in, and the Ti-sapphire laser was such a better laser system. Within a very short time, we got down to only these short pulses, but directly from a laser. And we got much more power than what we got with the dye lasers. And at the end, we reached the limit. And the limit, you know, when you are at 800 nanometer, where the Ti-sapphire laser is operating typically, the optical cycle is 2.7 femtosecond, and if you are in the 1 to 2 optical cycle regime, you're hitting the limit for the shortest pulse duration in that spectral region. Okay? So traditionally, these ultra-fast lasers, just based on the laser materials that were available, it was in this spectral range of around 1 micron when I go on a scale from all the way, this is all the electromagnetic spectrum, going from the radio waves all the way to the gamma, right? And then, because of these short pulsed lasers, we got also a lot of peak intensity. And the peak intensities were actually very useful for a lot of industrial application, material processing, for imaging. But the nonlinear optics in the perturbation theory actually allowed us to expand the ultrafast laser over a huge spectral range. So, for example, optical rectification or difference frequency mixing, the third order, will push it into the terahertz, and then frequency doubling, tripling, and so on will push it into the UV region. And with this kind of laser sources, a lot of dynamics have been learned over the years, and which on one side, I mean, in principle, there would be also a Nobel Prize should have been done in physics for this as well, not only in chemistry. So, and then in the early 90s, because of the progress that we made in ultrafast lasers, we left actually the perturbation theory in nonlinear optics, and high harmonics generation was discovered. It was actually discovered because, you know, people use these better and better lasers and were shooting into a gas target and then suddenly show very high harmonics, and it wasn't a decaying signal. It actually was leaving the perturbation theory. Some of the pioneers, I mean, Anne Lullier, Paul Corkum at this early stage. And that actually has been extremely successful of pushing the photon energy up to the VUV, so the vacuum ultraviolet. So you then started off still with the 800 nanometer laser, but you know, you got a lot of power into it. So you typically work with more than 300 microjoules with a peak intensity of a 10 to the 14 watt per square centimeter. And if you then go into one of these gas targets, you then get harmonics with up to, very easily, up to 100 eV, and with pulse energies, however, in the typical range of nanojoules. But because we start off with so much, there's still enough left at the end, and that was actually enough to actually also get the attosecond pulse duration. So that has been the driving here in this field. At the same time, you know, there is hope that we can push the high harmonic generation up in energy further, but you know, the number of photons we're getting, the efficiency is not very high. We're working on it. Meanwhile, the XFELs can easily produce that kind of, a lot of photon flux, high photon flux in this region, and easily can produce femtosecond, and they're working on getting attosecond. So overall, when you look at what we have today, we have, in principle, synchronized pulses going from the terahertz to the hard X-ray with atto and femtosecond pulse duration. It's a huge toolbox, and that will really help to unravel the understanding of what is going on in the material. So let me give you just one example. So during the femtosecond domain, people looked at at division. So the first step in division is extremely fast. So when it's actually based on this rhodopsin molecule that has been also widely studied during the 70s and 80s, and this is what the molecule looks like. And so when you come in with visible light, then you actually, within only 200 femtosecond, you actually make this molecule bend. So you have actually a light-induced mechanical switch on a molecular level, which you control with light. And then, of course, this kind of molecule is not sitting alone. It normally sits in a huge protein structure. And you know, the dream is that we actually incorporate such light switches, light-induced mechanical switches on a molecular level that deform this larger system, protein system, such that we make a structural change down here that allows this molecule to dock in, to do whatever this molecule is supposed to do, for example, for medical application. So normally in medical application, people used a lot the synchrotron, X-ray, but with not that much time resolution. And you know, when you go back to Francis Crick, it was saying, if you want to understand function, study structure. If a molecule fits in, it will dock on, and it will do its chemical reaction, its medical application. But a lot of things don't happen just statically. Certain things only work dynamically. And this is just one example where, for example, the future vision would be that you actually control the medicine in your body by a light, and then only there the medicine will be active. So to study such huge structures, the XFELs, the dynamics of it will be possible with XFELs. And then the question is, can you actually calculate the dynamics of something like that? And also there we made a huge progress. So these really large molecular systems traditionally have been studied with kind of a classical force field approach, which is kind of the blue region. This is the classical region where you also apply classical mechanics. And then the idea is, because this is such a huge system, you cannot treat the whole thing quantum mechanically, because in principle you would like, you know, you have atoms, you have electrons, so put everything into your system and then apply the time-dependent Schrödinger equation, and then your problem is solved, right? The problem is you cannot solve it, even with the strongest computer. So you have to find an approximation where you say, okay, the stuff that I believe is not so important, I can model classical. And the stuff that is truly quantum mechanical, I treat quantum mechanical. And so the balance to do that, you know, you have to make judgment calls, and ultimately you need experiments to confirm that your assumptions are correct. And you know, these kind of mixed quantum classical simulations, the QMMM simulations, actually recently were also recognized with a Nobel Prize in chemistry. So, but even if you go into this quantum mechanics, even if you take a very simple system, actually you still, when you want to have the dynamics, you still make approximations. So when you typically look where the typical approximations people do in quantum mechanics, there is only a few, there is more. But you know, you have the time-dependent Schrödinger equation with the wave function that describes your dynamics. So normally you cannot solve this. So what do? The chemists have been using the Born-Oppenheimer approximation, basically saying electrons move much faster than atoms, so let's do the separation of the wave function. Then what has been also very successful in many dynamics, you can reduce it to a single active electron approximation and look at the dynamics of the wave packet that has been extremely successful in solid state physics, electron transport in semiconductor, nanostructures, high harmonic generation, and molecular dynamics. Then another approximation is that we say, okay, I'll just look at the probability distribution of the wave function and the dynamics of this one. So you go from the time-dependent Schrödinger equation to the time-dependent dimensional functional theory, which is much easier to solve, but you lose the phase information. And when you lose the phase information, you lose something. So it's okay for weakly correlated system, but it's not okay for strongly correlated system. As you know, we haven't explained high TC superconductivity so far. And it's a complicated system. So the DFT has been also a success. So the chemists gave that one also a Nobel Prize. That was actually in 1998. And the belief was, oh, DFT is solving our problem. It makes Schrödinger equation very easy. But what happened since 1998? DFT has been a success story. This is the explosion of using this kind of codes to explain what is going on in chemistry, in material, in condensed matter. But, you know, people also realized over the time the phase information you couldn't just get rid of. And so people made a whole bunch of correction to DFT. And this is the alphabetical soup of corrections. And even the experts tell me it's sometimes hard to understand what approximations the different people do. And some of them make kind of arbitrary approximation, which maybe is not really justified from a physics point of view. So this is obviously a problem. So now with the move of being able to get attosecond time resolution, we actually have for the first time the possibility to distinguish between electronic dynamics and nuclear dynamics. And so we can actually test these approximations and give a true feedback back what is okay and what is not okay. Okay? And this is actually why this attosecond science is so important in my opinion, and will have a lot of impact in many, many fields from physics, chemistry, and biology. So this was actually also a reason why we got in Switzerland a national center in competence in the MUST, Molecular Ultrafast Science and Technology, because we got together 19 PIs all over Switzerland, 6 additional PIs at the leading house at ETH and Bern to actually address all these questions that I was talking about in an interdisciplinary fashion, going from physics, chemistry, and biology. So now let me go back to physics, because then you think, okay, the complexity and the open question in dynamics is only coming with more and more complex system. But actually, I can tell you, even fundamental physical questions when we go to the time dependence, the electron dynamics in the attosecond domain are unresolved. So let me take one example. A really simple example that you all know about. This is the how long does it take for an electron to tunnel through a barrier? You all in physics learn how this electron wave packet is going through a barrier. Not time resolved, but in principle. Right? We all solve the boundary condition, we can calculate the transition probability, and you can see that as the energy of this electron is moving up in the barrier, the transition probability goes up exponentially, and then above it, it will be 1, but you have some oscillation because of the wave character of the electron, which gives you some reflection at the boundary. So this is actually well understood, and when you normally as a student start saying, okay, that's the transmission probability, but how fast does it take? You know, I've been told when I studied, this is not the right question to ask. So it's always nice when you get older and you go back to the question that the people told you you're not allowed to ask. Okay, because if you get that answer, you should really think. Okay, so why is tunneling delay a problem? And it's still a problem today, actually. So there are some hardcore theoretical physicists who say time is not an operator, therefore cannot be measured. You have no observable. And you still have those when you try to get a paper published. So not possible. Then you have the other side and say, easy. Just follow the peak of the wave packet. What's the problem? this is then the group delay. People who do ultra-fast laser physics, they know everything about wave packet and the propagation of photon wave packet. So, you know, why should there be a problem? So, both of these answers are wrong. And this is what I want to explain to you a little bit in more detail. So, this is the typical thing what you do when I talk about follow the peak of the wave packet. You just take a superposition of plane waves coming to this tunnel barrier with a certain energy width, right? And that gives you the electron wave packet, and the intensity gives you the probability distribution of this electron. So this electron has a little bit of spatial uncertainty. And we know that this electron will propagate with the group velocity. And this group velocity is basically the velocity of the center, or if this wave packet is well behaved, the peak of the wave packet, right? So we send this electron in there, and then we ask, how long does it take? So you go in, then you look at a different time, you have the wave packet going, tunneling through the barrier, a certain part is reflected, so you have the interference, you see the peak of the wave packet is not so well defined, so you're not following the peak, obviously, because it suddenly makes a jump here. So you follow the center of it. But you still have another problem, and then it goes finally through, but you still have a problem. When does this tunneling process actually start? When do you say, okay, it starts here, and this is how long it takes? If you have an analytical function here, you know, you have signal already in the barrier here when it comes. So when do you say is a clear start, and when is it an end? So it's not so easy. But then some smart people say, easy, you know, you can just repeat the measurement. So let me just explain to you why the tunneling time that when you follow the peak of the wave packet is also referred to as the Wigner time. It actually goes back to 1955, where basically, you know, when a material wave goes over a potential, then we know while this wave is propagating through this, you obtain a phase shift. And this phase shift is then was also referred to as the scattering phase shift for obvious reasons, because of the experiments that you do. And when you look actually at the energy dependent of this phase shift, you know, when the electron has different energy, you will experience different phase shifts. And if you take the derivative with regards to the energy, you then get into the so-called Wigner delay. How long does it take for the wave packet to go through? And so this is actually then when you look at the peak of the wave packet or the center of the wave packet, and this actually corresponds also to the group delay, as we know from laser physics extremely well. Okay, so this is basically what we think, what some people think easy, just measure this group delay, right? So you take an experiment with a tunnel barrier, then you make the same experiment with the same wave packet, take the tunnel barrier away, and measure the time it takes for the wave packet to go through, and you look at the difference. That's the tunneling time, right? Should be easy. So it's maybe conceptually easy, but to make an experiment under the same condition for an electron, because it takes attoseconds here, with that kind of a measurement accuracy, to have a tunnel barrier and the next time you don't have a tunnel barrier is not so trivial experimentally. And what is maybe surprising to you is theoretically also wrong. I'll explain to you later why. Okay, then there is a paper by, this is all famous people, Büttiker, Landauer, 1982. So they approached the problem of when does this tunnel actually start and when does it end, is he put in a clock into this tunneling process. And so they proposed to oscillate the peak of the tunnel barrier, and when you then calculate the transition probability and you take the contrast, the transition probability at the maximum, height minus the transition probability at the minimum height divided by the sum, you actually get a tangents hyperbolica omega and a time. And then they said this time is the traversal time delay for the tunneling. It had the additional benefit that the scaling towards infinitely high tunneling barrier and infinitely narrow tunnel barrier actually made physical sense. And this is actually an explanation I got from Markus Büttiker directly, because that he was a professor at the University of Geneva, unfortunately died just recently. And he actually explained it to me when I got into this field to measure this one, okay? And then at least, this whole field of tunneling time is such a huge field. The best is you go to the expert and let them explain it to you, and that's what he did. So I took a picture from the whiteboard when he explained it to me. So there was another proposal, another approach to use light. If you use light and an atom, so you take your photon wave packet, a short pulse, they make the electric field in this light pulse so strong that you bend the Coulomb potential, for example, of a hydrogen atom, so strongly that an electron can be pulled out through tunneling, then you form actually the tunneling process with light. And there was a theoretical prediction, which goes back to Keldysh, actually in 1965, who predicted such a tunneling time induced by the light. So assuming at that time, of course, we didn't have this strong laser light to actually do this experiment, but he basically proposed the so-called Keldysh tunneling time, and he just used a linear approximation of this tunnel barrier, a triangular approximation. So at his time, the electric field of the laser is an F. If you study the Russian literature, they always used F for the electric field. So you have here this triangular barrier that is the electron is tunneling through. You have a certain tunneling length depending on the electric field of your laser. And then he proposes, you can actually go through, you actually can understand this one. You can actually then say the electron in the Coulomb potential has a certain average velocity through the virial theorem. And then when it comes out in this picture, the electron has initially no velocity. And then he basically calculated how much time does it take for this electron to go with this average velocity, which is half of the initial velocity through this barrier. Because you have the problem, if the electron goes through the barrier, it's a forbidden place. So what kind of velocity is this electron supposed to have? So he just assumed half of it, right? You can also do it with an integral, you get the same thing. And then you get the Keldysh time. It's another time. Okay? Now we produced short pulses. We produced strong enough electric field, so we wanted to measure this Keldysh time, right? But instead of actually using linear polarization, we actually used circular polarization. So when you use circular polarization in a short pulse, then you know that in a circular polarization, the magnitude of the electric field goes slowly up in a pulse and then down again. So it's slowly up, it's not going dung, dung, dung. The magnitude is going up and slowly down, but it rotates in the space, right? It goes around and then comes down. So if you go in the polarization plane, in the direction, a projection in the direction, you actually have the electric field going small and then going larger and then small again. So we basically use this principle as a clock. So instead of Büttiker with the oscillation of the potential barrier, we actually use the rotating electric field as the clock. So we know that if you have a circular polarized light, the electric field is rotating and actually gives you a macroscopic clock and a microscopic, because it's the same if you just have less than one ionization event in a dilute gas. So the clock will not change. So you have a time reference with the circular polarized electric field vector, which is acting as a hand of a clock. And we know from the measurements, the way we actually measure time in the macroscopic world, the faster the hand of the clock is rotating, the more accurate is your time measurement, right? And so if you go down into this 800 nanometer regime, you have more or less one revolution per femtosecond. So you have a stopwatch where basically 1 degree with a center wavelength of, for example, 735 nanometer gives you 7 attosecond time resolution. This is the most accurate measurement you can do. You can even do fraction of a degree measurement, right? So this is your clock. So, but then what do you measure? So we basically do this in a simple target in the single active electron approximation. We use a two-step model. The laser light comes and ionizes just one atom. So the electron tunnels through, and then as soon as it's tunneled, it will propagate and accelerated by the remaining part of the electric field. So if you then take in the polarization plane, as you explained it before, you see the magnitude of the electric field going up, and at the maximum, I assume now, the electron will come out instantaneously for now, and then will be propagating further within the leftover of the laser pulse. This is the center of your electron wave packet, a semi-classical model, because the trajectory then you describe with a classical model, which is the center of the trajectory, which is okay, because you have very little dispersion because you're far out after the tunnel barrier, and according to the Ehrenfest theory, it's an approximation which is valid. So you can actually show, theoretically, that after the pulse, without any Coulomb interaction, the electron comes out actually exactly 90 degrees when it came tunneled through at the maximum of the electric field. And because we want to know where is the maximum of the electric field, we actually go away for technical reason. I'm not going to explain too much, but we go actually to a little bit off the circular polarization. We go to an elliptical polarization, which is much stronger than what we used. We typically used like 0.9697 ellipticity, and then the time zero is extremely well defined. This is the most probable starting position, because that's the strongest electric field, and that's the highest probability, which is an exponentially dependence on the strength of the electron. So this one is simply a polarization measurement. And then you measure in the polarization plane in what direction the electron comes out. And that's a momentum measurement. And that momentum measurement you can do vector, you can do with arbitrary accuracy. And so you then repeat this measurement many, many, many times. So each of these dots is an experiment. You average over many, and then you look at the most probable distribution for the final electron. And if there is an offset, that must be because of the tunneling time. There is a small correction because of the Coulomb interaction, which is actually going back to Landau-Lifshitz. Solved. You put it in, and actually you can get, if there is a time delay, you can actually measure it. So when we started, Keldysh time for this type of experiment was in the order of 500 attosecond. It was long within one optical cycle, right? One optical cycle is around 2.4 femtosecond. The Büttiker-Landauer was a little bit differently, and when I talked to Büttiker-Landauer, he was really excited and was hoping we were measuring his time. Okay? That's why he also spent the time to explain it to me. So another way to explain it is actually through the Feynman path integral. Because, when people say, oh, time cannot be looked at in quantum mechanics, when you actually treat quantum mechanics with the Feynman path integral, then you say an electron goes through this barrier. You go through any possible path, and each path is deterministic and has a very specific time the electron is inside the barrier. So this is the dwell time. You measure, so you know, one possibility is going in and going out and going in, but you only take the time where the electron is inside, the dwell time, right? Of course, this trajectory where it goes in and out is not very probable, and certain ones are more probable. So you can then calculate for each of these trajectories a tunneling time and a probability. And then you get a probability distribution of tunneling times. And if you take the peak of this probability distribution of the tunneling time, this should be the same as the peak that we measure here. This is the most probable trajectory, right? And this is what we measure. So this is blue, our data point. This is a scale of 0 to 800 attosecond. This is basically the peak electric field that changes the barrier width here. And the blue line is the Feynman path integral calculation for a bound to a continuum state. So you think, wow, why did this news not shake up the scientific community? We didn't get it published in Science. Actually, I had one of these reviewers who said, you can't measure time. So I never got rid of this guy, or girl, or woman, or whatever. Anyway, but you know, there is actually something else. We have a perfect agreement with the second theory, and the second theory is the Larmor time. And the Larmor time is a Gedanken experiment. You know, you assume that you have a uniform magnetic field only in the tunnel barrier of this electron. And you know, the electron has a spin. It goes through the barrier, and the spin precesses in a magnetic field. And if you measure the direction of the spin before and after, you have the tunneling time, the dwell time of the electron, right? That is in agreement with our theory as well, also with our measurement as well. So we have an agreement with two theories, right? But we have no agreement with the Wigner. Here is the Wigner time, the Büttiker-Landauer time, the Keldysh time. And you know, there are strong opinions out there about time. So people, and there is a huge group of people who think it should be actually instantaneous. So anyway, so why not the Wigner time? I told you, I mean, why is it not? Why is that concept not even correct theoretically? Because you forget the phase. When we have an electron propagating, even in vacuum, it disperses. There's a chirp happening on the electron. And if you take into account the chirp, you actually have a distribution of the frequency as a function of time. And if you have an energy filter in the tunneling transition probability, you have the peak or the center of the wave packet makes a shift, which has nothing to do with the dwell time. It's simply a filter effect. And therefore, the Wigner time can't be right in combination with an energy-dependent transmission, right? So that's clear, that's easy to understand why this is not the case. Now, when you measure such a fundamental process, and there has been a discussion about this tunneling time for more than 60 years, people become very emotional, right? So I didn't do this experiment with hydrogen. As you know, for those people who have a little bit of chemistry, it's very hard to make nice hydrogen, and you can't get it out of a bottle, right? So we actually did the experiment with helium. And actually, we also used the adiabatic approximation. So what do I mean with adiabatic approximation? So I assume that this tunneling is so fast that I can assume a static tunnel barrier. And what happens if actually during the tunnel process, the electron actually absorbs one of these photons and then would come out a little bit at a different place. So there's a huge literature that goes even back to very fundamental theories going back to Russians, PPT, the K theory, and so on. It's an ongoing discussion. When we take all the theories that were available at this point and put it into our measurement and take into account non-adiabatic corrections, they're all within the error bars of our measurement. It will not change anything. In addition, you know, the tunneling time that we are measuring is actually pretty short, right? It's in the range of 100 or less than 100 attosecond on a change in the potential barrier of an optical cycle, which is more than 2 femtoseconds. So normally, that's a pretty good adiabatic approximation. And you know, so you know, the tunneling time, we basically measure it is slower than the speed of light that the electron goes through the barrier, and it's faster than if you would just take the average velocity that the electron has in the barrier and you would take it away instantly. It is faster, but it is not instantaneous, according to this measurement. Then the people say, oh, laser-induced tunnel barrier. That only works in the dipole approximation. Okay? So what is a dipole approximation? We all learn in school when the dipole approximation is that when the wavelength of the electromagnetic wave becomes comparable to the target of investigation, then, you know, we have to take into account the spatial dependence of the vector potential. So there is an upper limit of the dipole approximation at high frequency, which is well known. But when you look at and you go down, to longer and longer and longer wavelengths, there is actually also a lower limit in the dipole approximation. And maybe that's not so well known, and it actually has been predicted by Howard Rice that actually many of our pictures that we use in high harmonic generation, if we scale this to longer and longer wavelengths, actually this picture are falling out. And so the first breakdown is this magnetic displacement, because if you neglect the spatial dependence in your vector potential, your magnetic field is 0. So you neglect the interaction of the electron with the magnetic field of the electromagnetic wave, right? So when this magnetic field will become important, you know, when you have only the interaction with the electric field, then the electron in a linear polarized field just goes up and down. If the magnetic field becomes important, then in the moving frame, you start having this figure 8 motion. And the limit is defined when this deviation in this figure 8 becomes comparable to the electric field thing, right? As an estimate. And this estimate, for example, for 800 nanometer comes in when you get up in intensity, close to 10 to the 16 watt per square centimeter, which is pretty high for a laser lab at a university. But you can also get to this limit when you go to longer wavelengths with rather small intensities, already at around 10 to the 14 watt per square centimeters, right? And so what we did, we actually found an observable that tells you how the dipole approximation is breaking down. And so when we looked at the electron momentum distribution in linear polarization, and when we ionize it with a strong laser field, then we have always some electrons that were ionized after the pulse. You know, these are highly leftover excited atoms that will ultimately ionize in the imaging electric field. And they will be a reference of the ion frame, right? And when the rest is just the electrons that are being ionized through the laser pulse. And when you actually look, what we observed is we observed an offset under certain condition in counter direction of the laser. So normally you think the laser pulse is pushing the electrons forward, if anything, but it pushes the ion and the electron. But this one actually goes backwards. The electrons come out a little bit shifted against the laser. And initially it was a little bit surprising, but what we could show is that actually at 800 nanometer we don't see this one at all. And at 3 micron, the mid-IR, where we're approaching this dipole limit, the lower limit, actually this shift comes in. And we could show that we can explain this shift by the interaction of the electron also with the magnetic field. So we actually have an observable where we can say when is the dipole approximation starting breaking down. And why I say it's an observable for this is because we did this shift in the peak offset in the momentum of the photoelectron in the direction of the incoming laser field for many different targets, and it's actually very insensitive to the initial conditions of your thing. So the interaction with the magnetic field is so dominant, the small little differences of ionization potential, exit radius, and so on, doesn't matter. And so we have a pretty universal observable when do these dipole approximations start to break down. And obviously, then when the dipole approximation is not good anymore, then the picture in the length gauge with the tunnel barrier would be not correct anymore. But okay, with this experiment, we just confirmed one more time something that everybody was already saying. We are actually fine where we did this experiment. And now, if the physicists don't know anything but to complain about, then they say, oh, it's a multi-electron effect. Ah, that's a killer, right? Everything at the end is a multi-electron effect. Okay, yes, helium has 2 electrons. Okay, yes, we did the single active electron approximation. Actually, everybody expected helium to be very good in the single active electron approximation. You have 2 electrons in the S state. You pull one out, you actually would expect this, by all other ones, is very good. But if you measure such a fundamental process, you better be sure. There might be something else that we never looked at, right? So I had to say, yes, I'm not sure, right? I'm not sure. So the single active electron approximation has been widely used in the attosecond community. You know, this is this semi-classical 3-step model by Corkum that explained the high harmonic generation, where you come with linear polarization. You know, you have a noble gas and an electron bound, and the strong electric field bends it. You then have the tunnel ionization, then the acceleration, the electron recombines and gives you the high harmonic. And, you know, depending on exactly when the electron is actually coming to the exit of the tunnel, then the returning electron will have different energies. So the red is the highest energy. And, you know, in this semi-classical model, you actually predict for each energy level 2 trajectories, a short and a long trajectories, and of course these trajectories of these electrons going out and coming back depends on the laser intensity. And when you look at the long and the short, one has a little bit a shorter trajectory and the other one a long trajectory. I mean, it's a simple system to solve. Then actually people predicted, first of all, that when you look at the harmonics as a function of laser intensity, because you have a time dependence and a phase shift, you would expect a broadening of the harmonics, which were nicely observed with increased intensities. And you also predict that if you get both trajectories going and they interfere, then you're going to have a modulation of these harmonics, and the long trajectory are even more strongly chirped because it scales with alpha. So everything is nicely understood and makes sense, and we observed all of that and a whole bunch of other things. So the semi-classical single active electron approximation was extremely successful. And if something is successful, we forget it sometimes, right? But actually there is also a really nice experiment done where they used at double ionization. So when you do double ionization, you increase your intensity, and then it was always assumed, is this now non-sequential double ionization or sequential double ionization? So at the higher intensities, what was measured is that the 2 electrons come out independently. One electron comes out, and then you have the ion, and then the second one comes out. But at intermediate intensity, what actually happened is that the electron goes out, the first one, comes back, and then rescatters and kicks out the second one. So this is not independent, right? It's not single active electron. So there's an interaction between the 2 electrons, and that shows by having a higher probability with 2 electrons coming out in one direction versus in arbitrary direction. So this was a very nice experiment that actually explained this non-sequential versus sequential and actually clearly showed there was a breakdown of the single active electron approximation. So we actually used the Attoclock to measure the timing of the two electrons coming out. So the first coming out, and then in circular polarization, because the Attoclock is close to circular polarization. So this rescattering, if you pull out an electron with circular, it will not rescatter. So you would expect, with this simple model, there is no correlation between the electron. So you would say one comes out and then the next one comes out. But actually what we measured, it was significantly faster. So there is also, and when we look at the distribution of two electrons in one side versus in the opposite side, we did not have one. You see, we had very strong oscillation of this distribution. So this is also an indication that even in circular polarization, in this regime, in this intermediate regime, it is not a single active electron approximation. This result was later explained simply by the Coulomb interaction of the two electrons. So moving it out, and then still the Coulomb is a long-range interaction, and that one was enough to actually produce that. So maybe some of the complaints, this is a single active electron approximation, is justified, right? So initially, when we published it, we had our error bars going through 0, and it was systematically above, but you know, we had a lot of people who were very excited about zero tunneling time. And I know that people quoted this paper and said, I always knew it was zero tunneling. Then I said, no, but we only gave an upper limit. Okay, and of course we wanted to understand, is this now systematic or is this, and we improved a whole bunch of things to get this measurement, to ultimately get this accuracy that I was telling you about. And what is happening now, actually the hydrogen atom is the only thing that the people can really solve with the time-dependent Schrödinger equation with the light pulse. So there were a whole bunch of very famous people got together, modeled the Attoclock with the hydrogen atom, and predicted zero tunneling time for hydrogen. Oh, girl. Okay. Then, basically, with the end effect that now I'm building a hydrogen target, and I know that some of these theoreticians are working on a TDSC code which can handle 2 electrons, right? So stay tuned. We want to solve this problem. Meanwhile, I had somebody doing the same classical, semi-classical calculation that we used for the double ionization, just take into account the Coulomb interaction between the electron. We didn't see a difference. So if it's not the Coulomb, what is it? So I think with this example, I hope I could tell you how much excitement we have in the attosecond science. We finally are allowed to measure what people told me I cannot measure and not even ask. And what we are actually believing in the attosecond community is that photons will help to finally actually understand electrons. And you know, it's an interdisciplinary effort that will be beneficial to lots of fields. And you know, and that was the basic motivation for us in Switzerland to get also a national center of competence funded, actually, which lasts for 12 years. Will take us that long. And when you look at what is coming next in terms of the laser development, you know, ultimately we want to do attosecond pump probe. Right now, we hardly can do attosecond pump probe because in the attosecond domain, we have nanojoule pulses typically at 1 kilohertz. We have a microwatt of average power. This is not good for signal to noise, right? Normally, in the femtosecond domain, we have nanojoule pulses at 100 megahertz. So we are really hurting. You know, there's only a few preliminary attosecond pump and probe, but that is what we want to get. We also want to get higher photon flux in the soft and X-ray. I mean, the future will be that your generation, you will have access to lasers from terahertz to X-ray, even gamma rays. You're going to explain everything, right? At the same time, you know, the computer power will go up like crazy. And so this is also one reason why I'm working very hard. You know, there is lots of laser development. Generally, we want to get more average power. We're moving away from the Ti-sapphire laser, even though the Ti-sapphire laser has been a very good partner for us in our measurement. And because when you go up in repetition rate, you get average power. Average power means heat, and right now the laser material that is the best is ytterbium YAG. It's not a Ti-sapphire laser. We don't get the 10 femtosecond pulses with ytterbium YAG, and so we then need to do pulse compression. So there's lots of really exciting laser development going on, so I could give you an equally long laser talk, which I'm not going to do now because we're slowly but surely hitting the limit here. But I also want to tell you, I mean, I'm working very hard to convince our university to now invest in a larger laser technology platform, because, you know, as a single professor, even in Switzerland, you cannot afford a terahertz to hard X-ray laser. So slowly but surely, we need to get together, share the lasers, so that we can actually answer the scientific questions we want to answer, right? And so we're working hard to get this one going. Stay tuned. You might want to apply for a professor position when this one is up and going. And, you know, at the same time, there will be even more power available. This is the diode lasers that will be delivered to Eli to get to even higher intensities, and so we will unravel a lot of fundamental questions which going into astrophysics, nuclear photonics, and so on, and explain astrophysics things. And so I really think the laser physics is very bright in all respect. And I can say we have a lot of excitement, and, you know, it's a good field to get into. And with this, I would like to, of course, also thank my group, because, you know, without them, this all haven't been possible. I mean, we do laser development and we do attosecond science, and the combination of the two has been extremely useful for us over the years. And with this, I would like to thank you very much. I mean, sorry for a little bit.
Thank you, Professor Ursula Keller. I'm back chairman because I forgot, it was so interesting, I forgotten about the time.
Yeah, me too.
So one or two very short questions, we still have time. Please, Professor Valkunas.
Yeah, so I'm still thinking about the whole story about this tunneling time. So probably you are, in my understanding, that to measure this time, you need to define the momentum, as you define this. But if you have momentum, you are facing, then what about the positioning? So it means you are facing uncertainty in quantum mechanics.
Yeah, yes, I mean, so this is, of course, so what is the uncertainty, right? Because in this simple picture with this tunneling barrier, in this semi-classical, you know, when I go, let me go back, that's a good question to ask. Oops. I showed you the tunneling barrier so many times here, for example. You know, in this semi-classical picture, you then say, okay, you have an electron, and then you say there is an exit of the tunnel and has zero velocity in the adiabatic approximation. So you assume the electron is in a specific place at a specific time, and then you do this classical trajectory. Yes, I mean, it's Feynman path approach, you know. Each trajectory is
one path.
Yeah, it's one, but then you do averaging. But it is actually the way we are used to describe quantum mechanics. You know, people, at the end, what I measure with the uncertainty is momentum. And the electron comes somewhere out of the focus of my laser pulse in the gas jet. That's a macroscopic range. The momentum of the electron I can measure. The rest here, this is just modeling. I'm not making any measurements. I only do the uncertainty principle on the measurements. The time zero here is the polarization. I can measure that one. It's two independent measurements. And I have no restriction on the accuracy on these two measurements. So the only then restriction is in the model, how I interpret things. So with this model, I basically assume that I can split it up in a two-step, a quantum mechanical step, and a classical Ehrenfest type of propagation, which normally is okay because you're so far away. We changed the tunnel barrier from a few atomic units to 20 atomic units. So the electron is far away from this Coulomb. So the dispersion is very small. Normally, this is where the approximation is extremely well preserved. So I actually think, that's why people tend, in quantum mechanics also, they're very concerned, oh, you can't do this, you can't do it. At the end, you just have to say, what do you measure? And that's where the uncertainty is, and if you keep that under control.
Let me thank again, because it's already...
but I will be around.
If short questions, that's not like
I was long, it was my fault.
You have measured the delay time of the electron. My question would be, is the reflection of the electron with the 0 time or the same time delay as the...
Yeah. I mean, the key was here in solving this problem with the Feynman path integral was actually that it was actually the tunneling theory was done with the Feynman path integral before, but it was always going from a free state to a free unbound state, right, in the classical tunnel barrier. What basically Alexandra Lanzmann did, she calculated the Feynman path integral for a bound state to unbound state. And she did this properly. I mean, it's nicely actually taking into account all the phases properly, because you have to, otherwise you would not get the right time delay for the transition probability. So I hope that answers your question, and if not, we can happily talk about it during the poster session.